Hello, everyone. Welcome to today's webinar by Densify on top 12 Kubernetes resource risks. This is apparently a very, very popular topic. We've got an excellent number of people joining from what would appear all over the world, which is terrific. Andrew Hillier, our CTO and co-founder, is with me today. We are here in the sunny Toronto area. Looking forward to a rapidly arriving spring, although it's a little wintry looking today. Today's topic is one, as I said, of great interest. We are going to take probably a little less formal approach to today's content. Andrew is going to throw caution to the wind and spend a fair amount of time in product to actually surface the supporting info around his topic today. I think it makes it more real and relatable when you see it. And the essence of this session is really driven by the fact that as our customers scale to larger and larger environments with containers and Kubernetes, they're surfacing a fair number of risk areas that our technology is particularly good at helping identify and actually, bring solution to. So we're gonna dive in and cover this content. We'll spend a minimum of time on introducing, I think it's 2 slides on what Densify is, and then we'll get right at the heart of the matter. You can enter questions at any point through the console, and although we will reserve time at the end for Q&A, if there are questions pertinent to what Andrew's showing, feel free to enter them, and we'll do our best to interrupt him and field those questions. And he said that's okay, so we'll take him up on that. I think that's it. Obviously, everyone's on mute because it's a large group, but feel free to say whatever you want through the console. At the end, we will throw a couple of poll questions, and actually there may be mid-flight poll. I think we have 2 polls over the course of the content. So with that, let's get rolling. And Andrew, if you can just advance the first 2 slides. Many of you will know what Densify is, but for those that don't, we are a pure play analytics engine that is really focused on providing precise recommendations with respect to resources that will allow you to, without harming performance or without treating applications properly, make sure that you are controlling costs while ensuring that performance. So that is really what Densify is focused on. We do such within the overall stack of software that you might be using to manage, provision, deploy, and automate. Our goal is just to provide a constant flow of the optimal answers that allow you to balance cost and risk. That's really what we're all about. While we have a rich heritage in the data center, the physical data center, most of our focus today, if you go to the next slide, Andrew, is on providing these analytics and these answers in what is the capacity of the future. And in most cases, that's public cloud from one of the 3 or multiples of the 3 big public cloud providers, or Kubernetes-based container infrastructure, be it on-prem or in the cloud. So that's all we'll say from an introduction perspective. Obviously, if you have more questions about our technology, we'd love to hear from you after the webinar, but let's roll right into the content today, and that is looking at some of the scary things that you might have to deal with in the world of Kubernetes. Andrew?
Thank you, Chuck, and thanks everyone for showing up. As you said, we'll keep this interactive. If you want to ask questions, I'll be going back and forth to the product and in the slides. So ask anytime. I'm going to show a little bit of Amazon because obviously the containers run on the clouds, they run on-prem as well. And I'm going to try and give some insight into all of that, but I'm going to really focus on the right-hand side of this diagram. I'll try to show the 12. I might show 13, maybe 14 different risks. We'll see. We haven't really ranked them, but we can talk about that as well at the end. So let's dive right in. I am going to do a handful more slides just to set this up because I think everybody on this call probably knows, but the way containers work, excuse me, but in Kubernetes world, the resources are specified in a manifest, like you see the red text on the right-hand side here. So when you're starting containers, if the orange box at the bottom are the nodes, those could be VMs or cloud instances, they could be bare metal. Kubernetes will schedule the workloads, the pods and containers onto those nodes based on the specifications. And really all it has to go by is what you put in these files. Now, because a lot of times it hasn't seen any workload yet, so it just believes what you tell it. I need a quarter of a CPU or a half gig of memory. And the problem is it's hard to get those right. And we like to say it's kind of a head scratcher. I think it's absolutely true. Even if you do the best possible job trying to figure this out, you might get it wrong because there's an awful lot of data that goes into this. And I'll be showing a lot of that data. We wanted to go into the product because I'm going to show real examples. I'll try and give real insight from real situations we've seen in the cloud and on-prem. And the problem is if you give these specs and you don't quite get them right, Kubernetes is going to start your containers and your pods, and it's going to basically allocate resources to them based on the request values. And if you ask for too much, then you basically end up using a lot of hardware because, and this is important, these resources, it doesn't overcommit the same way a virtual environment will. So if I'm starting VMs on an ESX server and I give away too many resources, it will just keep giving it the same resource to multiple VMs. But containers don't do that. So in the container world, if we look at a cluster, if I'm starting containers, here's an actual cluster where 80% of the resources are given out to the container. So when you're starting a container, if you ask for a whole CPU or half CPU, there you go, give it to another pod and another pod, and you end up giving out all the resources, but they're not actually used. Because again, if you ask in this case for too much CPU or too much memory, then Kubernetes will give it to you. Once it's given out all the CPU or memory on a box, it will move on to the next box or the next node. And if your request is too high, your utilization looks like this. And this is an actual, we see this again and again in our customers. This one, I think the average was 7%. And oddly, a lot of environments kind of sit around 7% average utilization.
People never ask for too much. They never overestimate.
It's the right thing to do. I mean, if I'm starting an app and it's important and I don't know what it needs, I'm going to ask for too much. It's better than asking for too little. I might lose my job. Now, the truth is we see both, and I'll get into this in some detail. So there's too much and too little. Generally, net, we see too much quite a lot, but we see a lot of too little as well. You can see everything at the same time, and I'm going to show that.
Andrew, contrast when you ask for too much in the case of virtualization and VMware, what less difficult, right?
Let's say I have an 8 CPU box and I ask for a container, a scheduled container with 2,000 millicores. It puts it on the box, let's say the node. And then another one, once I've done 4 of those, it says, okay, I've given out all 8,000 millicores. I'm going to start scheduling onto a different node. In VMware, as an example, you can set your overcommit at 4 to 1 or 6 to 1 or 8 to 1. So when I give out 2 CPUs, I give them out again and again and again, and I can actually give out 64 CPUs, virtual CPUs. But that's not the way container scheduling works. The resources will be shared once they're running, but the gating process won't let you in if it can't fulfill your request. And that's a great point because this is 7%. A lot of virtual environments, we see the average utilization is like 40, 50% range on average, which is kind of about 8 times this because you are overcommitting. So it kind of works out in the math. So, I think this is kind of I'll talk about this in terms of all the different risks, but the fundamental problem is when we're giving out resources, if we give out too much, we will strand a lot of capacity. And that's kind of a financial risk. And I'll put that into the grand scheme of risks, but that's kind of starts to create a problem with money and also a problem with I'll run out of capacity. If I'm doing this on-prem, I'll just run out of servers before I've used them all. So I might not be able to provision. So with that base concept, I think we're going to go to our first poll, which I'm not entirely convinced I will be able to see as it comes up.
It's up now, Andrew.
Okay. Oh, there it is. So the poll is, are your container clusters well utilized? So based on what I just showed, if you know, do they look like the example? We see an awful lot of ones that like that. We see some that are better, but rarely. Are you better than the example? Are you great? You're doing a great job. If so, we'd love to hear how you're doing that. You have no idea, that's a perfectly fine answer, because what we're finding here is that a lot of people, there's a lot of data coming off these environments, and just understanding what they're doing, a lot of people haven't gotten to that point yet where they've been deploying containers in production, but they're not really going down to see that level. If you try and do it in Grafana, there might be 10,000 charts, so you can't really get a good picture. So not knowing, we see that quite often when we show this to people, they're seeing it for the first time. And there's definitely a problem in there, but they weren't aware of it because they're too focused on just the basics of getting the containers up and running. And I see the answers rolling in. I think it sounds like some people look the same, some people fewer look better, and then a lot of people either don't have many containers running yet or don't know what they're doing. So, which I think that's kind of consistent. We ask this question every time we give a webinar, and I think we get consistent answers like that.
We do see a fair amount of polarization in the market where just about everyone is doing something with containers, and then a smaller set that are hyperscale have gone really quickly. We expect growth to be significant. It's the way most are going, but there's still a lot that are dealing with a few, right?
Yep, absolutely. So I'm not sure if that's okay. The poll is closed, so I will continue on here. All right, so we've talked about the financial problem, which I think is the one that people tend to see first. Now, interestingly, you don't see it necessarily in the detailed data, you'll see it in the cloud bill, and I'll talk about that in a bit. But there's also significant risk. So here's an example, and let me try and explain what I'm showing here, because I'm going to show a bunch of these later on. The other ones will probably look a little more interesting than this one as far as the curves, but this is a memory utilization, a 24-hour view of the memory utilization of a container. And I won't get into the details of how this is based. We're doing a kind of a machine learning, the analytics of all the history and looking at all the patterns, and we build different models. But what we're saying here is that this particular container, the request value is 1,000 megabytes, so a gigabyte. So we're asking for a gig for this container, but you can see it's actually using 3 when it's active. When it's not active, it's not using anything. So we're not asking for enough memory on this thing, which might be fine. I'll get into some detail. Might not be fine. Depends on the bigger picture here. But you can see the analytics are recommending you should be requesting 3 gigabytes for this thing because you're using 3, and that's going to protect it from, so those resources aren't grabbed by somebody else and you getting killed, and that can actually happen. So this is an example of a memory curve. So even though my environment might be really wasteful and wasting a lot of money, I still might have risks lurking inside it. I'll show this in great detail. On the same workload, I might have too much CPU and not enough memory. It's all over the place. But memory is particularly interesting because when you talk from a risk perspective, it's not just a risk of spending more, it's a risk that you will get killed. And there's 2 scenarios for that. And this is just the OpenShift documentation. Kubernetes generally behaves this way. If you don't ask for enough memory and the memory gets exhausted on the node, it'll start evicting containers. It's that out of memory killer is what it's called. And so scenario number 1 is I'm running out of memory on my node or my server or my cloud instance. Something's going to get killed. I'll talk more about this in a bit. Scenario number 2 is probably even more insipid. It's that if I go above my memory limit, a process inside my container can be killed. And it doesn't say can be killed, it will be killed. And we've seen this happen. I can't show that data on this webinar as far as that actually having a field, but I'll talk quite a bit about it. This is like scenario number 2. So if I don't give enough resources, nasty things can happen, particularly with respect to memory. So again, I'm going to talk more about these. I'm going to show these in the data. But these, when we're talking about risks, these are what I would consider hard risks. There's kind of some risks are worse than others. These ones are some of the worst. So we, just to kind of back up for a second, we do this analysis a lot in a lot of different customers and environments, and on large numbers of servers, and containers. We've done 30, 40,000 containers in one go. And what we find is that there's an awful lot of data that produces, and this is part of the reason people may not know what's happening in their environments, because who's going to look at 30 or 40,000 lines in a report or Grafana charts? So what we did is we built a visualization, and I'm going to take a second to explain this, and then I'm going to kind of cast all the risks through this. So this is a histogram, a frequency distribution of my memory requests, whether they are correct or not. So the way you read this is the left-hand side, the y-axis, is the number of containers. So that green bar means that we've got about 23 containers in this case are correct. The memory requests are in line with what they're using. If you stray to either side, you're too big or too small. So the yellow means I've asked for more memory than I need, maybe a little bit more. 200% means I'm asking for twice as much memory, up to 5 times as much. So the far right is I'm asking for 5 times as much memory as I actually need. To the left, the red means I'm not asking for enough. That's the risk zone. And so, for example, that 35% bar means I'm asking for only around a third of what I should really be asking for, which is what I showed on the other slide. The request value was actually about a third of what I'm using. So we would fall into that bucket. And that's a pretty nasty zone, but you have to interpret it in the whole picture. The gray is unspecified or unset. There are some that don't even have values, which is, again, another problem. And if you consider that Kubernetes schedules things based on what these numbers are, Kubernetes is not going to know what to do with an unspecified, if you don't specify the request. It's a bit of a crapshoot at that point as far as how it's going to schedule the workloads. And again, I'll drill into some of these in the data.
What's the biggest environment you've looked at through this lens, Andrew?
I think the biggest I've personally seen is 38,000 charted at once, and it gives a really nice picture. It's more of a smoother bell curve, and it's that in that environment. We also then looked at each data center as a visualization with like 15, 20,000 containers each, and the cloud providers independently. So you can chart this at any level. I'll show in the demo. You can show a line of business. You can show a container, a specific container type. And the more you do, the more statistically it becomes like a bell curve. And the funny thing is, Chuck, that we've seen cases where some cases on the whole, you have the right amount of resources, it's just everything's wrong. I'll try and show that in the demo if I have time, a case where there's no green. Everything's either too big or too small, but you're kind of on average okay. So you're lucky. You're getting by because you're screwing up in both directions the same amount is effectively what that is. So we see that quite a bit. Although usually there's a bias to the yellow, meaning you're kind of messing up on the expensive side. So again, I'm going to show these live in a second. So not set, too big, too small, not set. And obviously the red is dangerous. The yellow is wasteful or expensive. And as I mentioned, we were on a call with an analyst who was pretty insightful about this, and he's kind of really wrapping his head around this and saying, yeah, well, if you're sitting at 500%, you're going to exhaust your quotas. You're going to use up all your quota before you actually do your work because you're just asking for way too much, way too much CPU or too much memory. So it's more of a hard risk too. There'll be some point where you can't provision another workload because you're out. Or if you're on-prem, of course.
And it's largely a function of these decisions being made at an individual level by people, right? I mean, there's no reason that this has to be the case.
No, absolutely. That head-scratching stick man at the beginning, it's true. It's just who's going to know. People don't have time to think about how many millicores. I was joking, Chuck, you might recall another webcast we did a while back where I was saying, if I had to tell you how many millicores Outlook needs, I have no idea. I use Outlook every day, but I have no idea. So even the most educated, smartest people probably will not be able to set those values properly because they don't have the data. It takes analytics. It takes a whole lot of analytics to figure this out, which I will go through. So even if you're trying to get it right, you probably won't, or you'll probably err on the side of the yellow. Is what tends to happen.
When you get to the memory portion of the discussion, someone's asking how Densify helps determine correct memory request size. Is it retrospective or can be preempted using Densify? It's an interesting question because the answer is yes to both, right? Once you have
absolutely, yeah. And we build out all kinds of historical models and it's policy driven. So I'll try and speak to that as well, where a prod workload might have a different risk profile than a dev test workload. So the request value for prod might cover more of the workload pattern than a dev. Dev, you might be able to be a little more liberal with the resources and overcommit a bit more because it doesn't really matter. And it also depends on CPU versus memory, which gets to this chart, which is the 12. The 12 really comes from the fact that we have mainly 4 different resources that need to be specified, and each of them can be too big, too small, or not set. So each of these starts to give a different scenario in terms of the risk profile. And I'm going to go through these, but I'm going to go through them live. And so let me just queue up. Let me flip over and make sure I can flip over to my demo now. Can everyone see the demo?
Yep.
So quick orientation. I'm not going to spend too much time going. I'm going to go deep, not broad. If you look across the top, there's public cloud, containers, private cloud. There's, again, I'm not going to nearly go through all of these things, the automation policies and stuff. I'm going to spend all my time in containers, except for, you'll see here just in the cloud view, this particular server is analyzing workloads from Amazon, Azure, and Google. And you see there's EC2, RDS. And I'm just going to zip into the scale groups for a second, just to make a point. So this, we're doing a pretty deep analysis, a very deep analysis of these scale groups, and I'm not going to go too long on it. But if I just click on this 4th one down, or is it which one did I want to show? The 5th one down. Here we go. So here's a scale group, and the reason why I show this is because this is what the containers are running on. So this is where the costs show up. If I make a mess of my containers, I have no idea what my containers cost, but what happens is one of these scale groups gets really big. Again, on-prem, you'll just run out of capacity. In the cloud, you'll probably just run more and more nodes and get this giant bill. And here's a scale group that's running, it's running 4 nodes on C5 larges, and the min and max are set to 4. This is a real environment. So you can see the scaling activity is just pinned at 4. But we're saying, if you go and replay all the historical data by hour, so these are, I should have mentioned, these are by hour. So the model shows a 24-hour review. That's a model built on analyzing history based on different analysis techniques. So it could be the worst, it could be a typical day. What we're saying is if we replay history through this thing using M6I larges as the node type, we see that we'll need between 2 and 4, depending on the time of day, to service the workload. So we're going to recommend the new instance type and new scaling parameters for this scale group. And I want to show this just quickly before getting containers, because I'll circle back at the end. This optimization is kind of this is where the rubber hits the road in terms of what you're spending or whether you have the right amount of resources on the floor in aggregate. But to get this right, we have to get everything inside it right. Because if all your requests are wrong, I might need to run 10 nodes to get enough capacity to run my containers. So I wanted to show this first because the scale groups or VMs on-prem, like their optimization depends on what's happening inside the containers. But in this case, detailed scale group analysis to show me that the actual infrastructure I'm running my containers on can be optimized. And you can see there's all kinds of weird and wonderful patterns here, ones that need to be bigger and smaller. And that's a subject probably for another webinar. But that's kind of the supply side of the container picture. Now, let's drill into what's inside those scale groups. And I must have waited too, I didn't log out. I'm sorry. This is the beauty, Chuck, of doing a demo.
That's why I said you were going to fly close to the sun here.
Yes. Well, maybe we got my obligatory problem out of the way early in this case. Now, Chuck, I assume you brought some good jokes to tell just in case this would happen.
They won't be needed, Andrew.
Yeah. All right. Let me make the screen a little more full screen here. So, okay, so here I'm looking at the containers now in this environment. So again, you can picture them. There's the cloud, the infrastructure, the instances, the scale groups. Now I'm looking at the containers, which is a much more granular view. And in this analysis, I'm looking at 432 containers that are in 310 pods with 212 startup configurations. So I'll just spend 1 second on that. So picture Terraform files. I've got 212, say, or Helm charts or whatever the case is, that define the configurations, and I'm launching them and stamping them out, a bunch of instances of them, and inside them there's a whole ton of containers. So some of the pods have multiple containers, obviously, and we're seeing all these different recommendations. Some are too big, some are too small, some are both. I'm not going to spend here. I'm going to go right down into the details and just go to the data. So if I click here, now I'm looking at the 212 broken down in this case by business unit, and I can look at them all kinds of different ways. I can view by quota or by namespace or by cluster. I'm just going to stick to business unit for now because I don't want to spend hours demoing, but you can see these are different business units. They have different numbers of containers. Some have risks, some have opportunities, and you can see all these nice color-coded things telling me. And I actually get an efficiency ranking saying you're not doing too bad. Your new accounts business unit, you're almost right on as far as your resources. But if I look inside it, they're probably terribly wrong at the container level in all directions. That's what we see, and so I will do that in a minute. What I'm going to do here is actually click on the 212, which is the whole environment right now. I'm just going to start with the whole environment. And what I get is 4 of those histograms. The CPU requests, top left, memory requests on the top right, CPU limit, bottom left, memory limit, bottom right. So I can actually see all 12 things I'm going to show right from this view because I've got red, yellow, and gray in each of those areas. So this is the entire environment, and again, you can see, like I said, the green means, yep, it's pretty good. We see in some cases, I'll try and show on where there's no green at all. Actually, nothing's right. In this case, we see a good bit of yellow and a good bit of red and different profiles for each. So I'm going to start diving into the 12, and I'll go back and kind of frame it as I go. So let me just, first of all, I'm just going to go and zoom in on just the CPU requests and make it nice and big so everybody can see this better. So out of all my launch configurations in this case, and actually, sorry, no, out of all my containers, I've got 141 that are actually okay. And then I've got a bunch that have not enough CPU and too much CPU. And let me go into the too much first. So this 500% means I have 59 containers that have at least 5 times more CPU assigned to them than they need. And if I drill down on this, we call this a stranded CPU risk because, again, if we run like that, we're going to give out a lot of CPUs and not use them. And that's like that scenario I showed in the PowerPoint. So I'm going to click down on that, and I quickly get to some high level of detail on these containers. Now, let me pause for a second. So by the end of this, you'll fully understand what all of this means. One of the reasons we made the histogram is because we were doing this on 25, 30, 35,000 containers at a time. And of course, that's a lot of data. So the histogram lets you see huge environments in a glance. Okay, I got it. I understand the profile. It's like a Rorschach test. You can kind of see, you can kind of see things very quickly in those views, and then get down to the level of detail, and I can filter down and all this stuff and just view my app or whatever that is. Right now I'm looking at the whole environment, so there's kind of 5 pages of answers here, but if I look at this top one, we're now in the CPU yellow zone, meaning I have too much CPU. Again, if you look at this curve, this is the 24-hour model of what the CPU is doing on this container. So it's going up and down between nothing and 250 millicores. And these little bars are quartiles. So all that means that the bottom is the minimum, the top of the thin zone is the maximum, the median is the middle, and the fat zone is where you're spending half your time. So you're going as low as 0, as high as 250, and you're spending a lot of time just below 250, kind of is what, by hour of day. So this is kind of a tiny one to see it on, but hopefully you can see that. So it's quartiles by hour. So this thing's using, on average, 152 millicores, peak around 250, we're giving it 2,000 millicores. The yellow line is the request value, the purple line is the limit value. I'll talk about limits in a minute. And we're suggesting, yeah, that's a lot. Maybe you should just be giving it, in this case, we're recommending 400. And this is driven by policy. So where this line lands, I can tune it. I can say, is dev, just put it lower. It's production, leave it really high. I worry about this thing getting busy, or I've seen it get busy at month end, so I'm going to set it up. Whatever that is, it should be done scientifically, not by guessing. And you rarely want to set the request and limit to the same value. That's kind of a different problem. So we're suggesting that it needs to go down. And the policy also says how aggressively you do that. You might want to just go a bit at a time and kind of work your way towards the right answer. Now that's an interesting one. Let me go down to I think this one. Yeah, okay, this is a good one. So, and you can see all the numbers here. The CPU request. This one is 4,800. So almost 5 CPUs. You can see on the purple line here, we're asking for almost 5 CPUs. Or sorry, no, my apologies, that's the limit. The request is 1,000, so we're asking for a whole CPU in this case. But on average, it's using 24 millicores. So what's that? That's 40 times too much. So it's you know, this is kind of crazy. I'm asking for 40 times more than I need. Now, the reason this happens is, we see this a lot. I call this a fallacy of insignificance, where somebody thinks, well, this thing's tiny, so it doesn't really matter if I get it wrong because it's tiny. But if you run a lot of these things, it really matters. So again, we see this again and again. Something that doesn't run very long, or something that is just a tiny container. What if I'm, you know, double or triple wrong on something that's really, really tiny? Who cares? Well, it's going to add up, and we do see it adding up quite significantly. You know, in real cases. So, you know, if I click around, you'll see all kinds of these where the values are way higher. You know, this one's 35. It's averaging 35 millicores. We're giving it 1,000. So that causes a lot of that overspend. Even though, again, each individual one, not a big deal. It's just a tiny container, but it adds up. So that's the CPU in the yellow. And again, this tends, especially this top one, we find that tends to be dominated by a ton of small containers that are missized. The red zone is the opposite problem. So I haven't given enough CPU in this case to that instance. So in this one, you see if I click through now, I get different looking curves. Let's just go to one that looks interesting here. Okay, so here's a pretty interesting workload. So this workload, the way you interpret that blue curve on the bottom left, this thing kind of fluctuates between very low, almost zero utilization, and half a CPU up till 9 a.m. And then it kind of goes up and uses almost 2 CPUs, kind of varies up and down within the hour, and then comes back down around 4 p.m., lands back down. So it's this is kind of a transactional looking workload. We see this a lot, like in banking apps and things like that, or reservation systems that are kind of, you know, their busyness is kind of driven by the general public being awake or being at work or whatever the case is. And you see again, the yellow and purple lines are dotted, meaning they're set to the same value. We're suggesting the next curve over in the green one that the request value should be quite a bit higher. And this again is based on policy. So if this is a dev workload, maybe I'm okay low. If it's prod, maybe I want it to be way at the top. If without setting that higher, we're not protecting this workload. And so somebody else could take the CPUs and from me as a busy time of day. So there's a risk of not giving enough CPUs, and I could get throttled. So that's the that's one example. I think there's another one here. I believe it's this one. Yeah, this is an interesting one too. This is a scheduler, it looks like from the name. So this thing kind of lights up every few hours and does something, and then when it's not lit up, it's sitting at about 150 millicores. So we've requested the yellow line looks around 240 millicores for this thing, but that's not enough for when it's busy. When it's busy, it's actually pretty busy. We might want to make that higher. And again, this is where policy is so important. How high you make that, it should be very deliberate. It should be based on policy, not guessing. We want this thing to behave properly. We don't want to to have performance problems. With CPU, generally you'll get throttled if you start running low on CPU resources. So that's the red. That's the red. The under. I'm just going to show you also the unspecified. So if I go into, I'm just going to search for unspecified to find it faster. Here's one that doesn't have a CPU request value, so it's kind of not protected at all. If you think about this, what is Kubernetes going to do with this? How is it going to schedule it? Let's go on this one because it's bigger. Here's one that's using almost 2 CPUs of resources at its peak. I didn't tell Kubernetes that. Kubernetes has no idea what this thing's going to use, so it's just going to slap it onto a node. And when it gets busy, we'll see what happens. That's basically what's going to happen. You might be okay because you might have a lot of other ones that are sized in the other direction, like wrong. But this is a risk. So the gray zone if I go back up to the, let me just get out of this and go back up to the gray zone is undefined. We don't really know what's going to happen, and we're just hoping we'll get lucky, I guess. So let me go back and frame this back in the, and I'm just going to try and keep it on time because we're actually getting through this running through time pretty quickly. So from a CPU request perspective, I either have financial risks or I can have certain performance risks that occur if I get them too big, too small, or unset. So let's step back. I'm just going to go back to the 4-pack here and kind of my apologies, CPU and memory, and kind of start going through these kind of just at this level now. So we did a deep dive on CPUs. Again, the risk here is throttling. Memory is a little bit different. So if I don't ask for enough memory, I get the same problem that I strand. So again, if I just look at this one, now we're looking at the third curve in the blue curve. I've asked for 8 gig and I'm only using 4.5 gig. And I'm pretty consistently using 4.5 gig. We've never seen it use more than 4.5 gig. Your policy could say give it a little bit extra for safety. We're saying give it 5.5. Don't give it 8. You're straining memory. So this is going to cause money problems again. And either or will, a CPU or memory being in the yellow will cause the same money problem. So I can have all kinds of weird and wonderful problems. And again, we see different patterns here. Here's a slightly bigger one. Here we're asking for a gig. We're only using 46 megabytes. So we are about, I don't know, what's that, 20 times too big on a memory request for this one. Again, may not seem like a problem one at a time, but it's definitely a problem in scale. Now, the far more interesting one for me in the risk is this red zone. Because it's a real risk here. So now what we're saying is, here's a case where I've asked for 2 gigs, and I'm using 6. So let's just picture the scenario, for example. So I've only asked for about 1/3 the memory I need. So I start starting these containers on nodes, and let's just say the node has 8 gig of memory. I can start 4 of these containers on a node, and Kubernetes thinks this should be fine because I've only asked for 2 gig. Well, when this lights up, which it does, looks like it's lit up as soon as it boots, if I run 4 of these, I blow the box right up. And what happens is it doesn't just throttle. You can't throttle memory. You get killed. That's that memory killer. So this is a real problem. Now, again, if I go back up to the analysis at the top, because I have a bunch in the yellow, and my net is actually, I have a bit more memory than I need in the environment, I might get by. I was just looking at one that's in this 1/3 what it needs kind of area, but I've got a bunch of ones that are also wrong the other way. And so I might get lucky and my node might have enough memory, or I might not. Same with unset. I won't bother drilling down on that one. If I didn't set the value at all, the same thing happens, even a little more severe. It's that Kubernetes has no idea what to do with it. And again, I will probably only work properly if I have symmetrical error. Here, we're kind of getting lucky that we're not having problems. So those are the request values. Again, they create a certain, they create a lot of the financial risk. They also can create operational risk. The limits are a bit different. If I look at the CPU limits being too big, we call this a runaway process risk because we're just asking, okay, here's one that's using 20 on average, like what is this, 40th of a CPU, but we're asking for almost 5 CPUs. Or sorry, we're not asking for, we're asking for 1 CPU. The limit is 5. So if this thing has a runaway, if it's a runaway process, it's going to use up to 5 CPUs. Now, it might stop at 1 if it's single threaded, but you might get lucky. It might go all the way, it might run all the way up to 5. So this is kind of a noisy neighbor risk. If I make those limits ridiculously large and that app has a problem, it can run up to the moon and it might hurt the node. Again, so it's just a bad idea to leave things that unconstrained in the upward direction. So CPU limits being too high means I can get a runaway process. CPU limits being too low, you will get throttled. So let's go look at one of these. I don't consider this the biggest problem. Well, in this case, it might be. Here's that transactional app again. It's going to get throttled at a half a CPU. It will likely get throttled at half a CPU. So if this thing is indeed transactional production workload, that's not a great idea. You're gonna have some weird performance problem happening there. The limit should at least be the top of the observed workload in this case. So all kinds of problems with this one. And again, this kind of curve implies it's production. You don't usually see dev workloads that look like this unless you have a really good load generator. So that probably in itself is a direct problem. And again, the gray, the unspecified, if I look for the unset values in here. Similarly, same thing, but even probably worse. I just didn't constrain this at all. This thing can run to the moon. So the limits, CPU limits are kind of, they can be way too big, and I just give you too much headroom to run. Or I do small, you get throttled, they're unset. Again, similar problems. Now memory, I want to focus on this one for a minute because this one is and I'm watching the clock and I'm running a bit long. This one is probably one of the most interesting. So let me just kill off this filter. If I look at the memory limits, this one has a lot of headroom to run up memory. So this one, if it has a memory leak, will run up to 25 gig of memory, even though it's only using 2.5 gig right now. So this again, memory, you can imagine if the memory is unset, this thing can run to the moon. And we've seen that happen. We've seen cases where there was a memory leak on a node, the container didn't have a memory limit set, and it kept going up and up and up until it used the whole node, right? And then what happens is, and I'll try and illustrate this in the curves, if I don't constrain, if I get too much, or I don't constrain on memory, the memory leak means it can go until it's the whole node, then this stuff gets killed. Then the out-of-memory killer will go after the things that are the furthest in the red. So that's the other reason you don't want to be in this zone, because even if you look fine generally, if there's a memory leak, you will be killed. So these start to interplay with each other. I don't want to see yellow, too much yellow here. I really don't want to see gray here. That's kind of poor hygiene. You should set limits on everything. And if you don't, then you could have a memory leak really ruin your day at the node level. So I know I'm showing a lot of stuff here, but hopefully this is making sense. Each of these has their own little profile. I'll summarize it in a second. And this one is possibly the most evil. So if your memory if your memory limit is too low, like I showed in that OpenShift guide at the start, something will get killed inside your pod. A process will get killed. So here's a case where the memory limit is a gig, and 4 times a day we're going up to 2 gig. It's probably doing something important, and guess what's going to happen? Linux is going to chime in and shoot a process in there, and we've seen that happen in the field. We've seen the memory data running along, and at an exact time it goes down to where the limit is because the kernel, it's not necessarily Kubernetes, it's Linux at this point, kills something to make sure you stay within your limit. So this one, again, I know I'm going quickly here now. This is pretty evil. That purple line is intersecting your memory curve. You kind of want to deal with that pretty quickly. So that's this red zone here. There's not a lot there, but we see things there. And if you have production workloads that are sitting there, get out of Dodge. You got to fix that very, very quickly. So that's kind of the kind of walkthrough. Let me go back to here and just kind of pull this up quickly so we don't take forever. So if you kind of characterize these, there's varying levels of risk. The one that I think is most scary is that memory limit, but also unconstrained, unlimited memory configurations in general can ruin your day. Your memory requests being too small. And just for completeness, which I'm not going to read all this out. Again, this is for reference for if you want to know afterwards. The different types of risk that these scenarios. So I showed all of these kind of in the demo, but really they're a financial risk or a performance risk, and that can mean, I run out of quota and I can't provision, or something gets killed, or something gets throttled. There's a whole slew of reasons why that can happen.
We actually have a poster in production around this set of information. It's not ready yet, so I can't offer it for download, but it is something that we will have available just for a deeper reference on these issues.
And Chuck, this would make a nice poster. I mean, everybody loves just a PowerPoint slide printed out black and white and stuff on their wall. Let me take, I know I ran long here, let me take 30 more seconds. So the name of the game is, the way to fix this and get things in the green is, I showed all these numbers, I showed all the recommendations. If you do them, the containers will have more sane configurations, more in line with their actual resource utilization. Kubernetes will automatically work better. It will schedule better because it's getting better inputs for what it's doing. Usually that means you run on less. Back to the scale groups I showed at the beginning, they'll get smaller. And then then you can say, well, and once I fix this, I might be able to go to a different configuration. This is that scale group recommendation I showed with a C4 large to an M6I large. So I don't need compute optimized. I can just use regular, or I can use memory optimized and get a better fit for the workload. So fix the containers, then the nodes follow. And here's an example of a customer that is a great example, did exactly this, where I'll just pull this all up. They hit our APIs using a bunch of cool sounding software, update the OpenShift templates every time a container deploys, and they're automatically fixed. So you don't have humans scratching their heads around what to do. They just rifle through the pipeline, and they're constantly optimized. And the beautiful thing is, when we rendered their histograms, they're some of the best we've ever seen. Like they're almost all green. The reason why they're not all green, by the way, is because the policies, in some cases, don't go too far. You want to kind of not really make big changes at a time. So if the policy is conservative, kind of low touch, it's just kind of work towards the right answer. So it might take a little time for all the yellow and the red to go away. So you don't want to move too quickly. But this is a great example, and there's a case study on our website about this customer and how they did this. And with that, I'll hand back to Chuck. It took 10 minutes longer than I wanted, but hopefully that all made sense.
Hit one more click there, Andrew. The text didn't come up, but I think the the takeaway from this is that there's lots of stuff that lurks under the covers. There's no reason to have it lurking in an infrastructure when analytics can answer the question. So humans, are good at lots of things, building the business functionality, et cetera, fitting to business. But these are questions that can be answered by analytics. I did want to call out that there is an offer in the market by Intel called Intel Cloud Optimizer. It's Densify. It's this software. Intel is so interested in making sure that their customers are selecting the right instance types in the cloud to ensure the cost performance balance. They'll actually, for the qualifying organization, fund Densify for a full year. So it is something that you might want to chat with us to see if your organization qualifies. The QR code there is a great way to contact us and say, hey, do I qualify? There are virtually no strings attached to this offer. They're just interested in their customers having the best experience on Intel-based infrastructure. So welcome the conversation around ICO. That's what we call it for short. Andrew, if you go to the next slide. A quick poll as we close. Simply, would you like to chat with us, or you're just browsing? I like that choice. Always interested to hear whether you would like to hear from us. I will point out as well that the FinOps Foundation, if you're not a member, it's worth checking out. I think we have a slide here with the links after the poll. They actually have a session specific to finance or FinOps and containers tomorrow midday. So it's actually very timely given our topic here. Can we close that poll and put up that slide? Yeah, here we are. So this gets you, it's not hard to type FinOps into your browser, but I did notice that their session tomorrow is all about containers and best practices. So you might want to check that out. And I think there's one more slide and just some other links with respect to some further materials, as well as actually that video is the one that Andrew shared on Raiffeisen. And if anyone has questions, I know we ran a little long, but if anyone has questions, we'd be happy to field them. And you can go to the next slide, Andrew. I think it just gives links to our social channels. Yeah, there we are. It doesn't look like there are any further questions. I think we will give people their time back. But thank you all for your attention and attendance today, and wish you a very good remainder of your day or evening. Thanks, Andrew.
Yeah, thanks everyone.